Now in this final video for day 68, I'll be talking about the bonus problems that you'll be given on the test tomorrow. I won't go in depth to these, but of course you can do a search on your own to look for extra help on these. But again, we're going to be finding the area between two or more curves rather than just finding the area underneath one curve over or under the x-axis. And so what I'd like to point out to you here, and we'll use number 22 as an example, is that these two equations produce two curves, and the two curves are shown here in the graph, and we would like to know what the area between those two curves would be when bounded by these particular x values. So we've got an x value of -2 and -1 in this case. That's what produces this this boundary on the left and the right hand side of this gray region. And then we've got the equation y equals 4. Well, that's this one up here, so we've got an upper boundary now. And then finally the equation y equals -3 over x squared, and that's what produces these two curves here. Now we're not that interested in the curve that shows up on the right hand side. Instead, it's just this one on the left, and that's what has captured this area here. So we'd like to know exactly how much area is captured by those curves. Now, the way I think of these problems is that there's kind of this cutoff point on the x-axis, if you will. And what that does is it produces an area above the x-axis. Now, this red area here is quite literally the integral of the upper curve. So the integral from -2 to -1 of the function y equals 4 with respect to x. And to that we would like to add the area underneath the x-axis, which is this section here, and that's found by the integral from -2 to -1 of this function, -3 divided by x squared with respect to x. But the only catch with that is that this area in blue, when it's drawn underneath a curve, is not a positive number. It's a negative number. So we are adding a negative form of this. Or, in other words, we could ignore this addition sign altogether and literally subtract the antiderivative, or I'm sorry, the integral of the upper function and the integral of the lower function. And that indeed is how we would compute the area between two curves. That area can be found by integrating the difference of the two functions. So rather than computing two separate integrals, that's not always beneficial to us. This one's not too bad since we have a rectangle on top and then this other irregular shape on the bottom. That's not too bad. But sometimes it again just makes sense, since we have the same boundaries of integration here, just to write a single equation. So the area would be equal to the integral from -2 to -1 of 4 minus -3 over x squared with respect to x. Now this turns into an equation that we have had lots of practice integrating, and I'll continue doing that without commentary. Oops, sorry, I think I forgot to hit the record button there. I just reminded you that we found the area to be 5.5 units in this irregular region here, and hopefully that makes sense. We had this rectangle on top that had an area of 4, and then this irregular region down below had an area of 1.5. Let's take a look at the next example. Now this one's kind of nice because the two equations are mirror copies of one another. We've got this upper equation that's kind of the boundary shown here in red, so that's going to produce all of this area, and then this lower equation produces this boundary in blue, and we're interested in the x equals 0 and x equals 4 boundary lines. Well, that takes care of this left-hand boundary and right-hand boundary, and so we're looking for the total area of the red and blue combined. Now, since these are mirror copies of one another, I could just calculate the area of one of these. This one would be pretty easy to do, and double it. Now that's the technique that I showed in the answer key up here. I literally just doubled the integral of just one equation. But if you use the subtraction method, as I outlined in example number 22, it would look something like this example in 23. Now I do realize that the equations are just a bit different, but you could still compute example 24 much the same way. So I'm going to leave that as an exercise to you. Instead of the integral from 0 to 4 of 2 times the square root of x minus a negative square root of x, I want you to find the integral from 0 to 4 of 2 times the square root of x minus negative 2 times the square root of x with respect to x. And I encourage you to calculate it this way, and then go back and check your work by calculating it this way, doubling the integral from 0 to 4 of just the upper function. These two should come out to be the same. Let me know what you think.